Now, let us see the importance of impulse response for a system which is an LTI system, that is linear time invariant system. Actually, the output of a system for a given input which is a impulse function is very important, in that when I calculate the transfer function, either Laplace transfer function or a Fourier transfer function of a delta function, the output is invariably 1. That means, when I feed an input to a system, then what happens? X of t given delta of t, then h of t will be y of t, because I said Laplace transform delta of t is 1 and Fourier transform delta of t is 1. That means, let us take a block here. Okay. This is x of t and this is y of t. This is the input, that is output. Then let us say this is equal to delta of t. Then we call this as impulse response. That means, how will the output behave when an input is an impulse response. In other words, if the transfer function of this is h of t and the input x of t is delta of t and y of t is the output system, then for an impulse system y of t will be nothing but h of t, because the Laplace transform of a delta of t is equal to 1 and the Fourier transform of delta of t is equal to 1. So, let us just see this impulse response, the output system for a unit impulse input. Unit impulse response is very important in the sense, if x of t is equal to delta of t, output y of t is equal to h of t. Then L of delta of t is equal to 1 and f of delta of t is equal to 1. So, that is a system how it behaves when you apply a input which is a delta function. Once the transfer function of LTI system is known, that is h of t is known, then S domain what happens? Inverse Laplace transform is the impulse response, and frequency domain the inverse Fourier transform is again a impulse response. Now, let us see the response of a linear system. The output or the response of any system can be obtained by convolving the input with the impulse response of the system. So, let us take a system. Okay, this is our linear system. Let the system have a transfer function h of t. Let input be the x of t and output be the y of t. Okay. So, this is my input, this is my transfer function, this is my transfer function and this is my output, or it is also called as the response. Okay. So, these are the terminology which we are using. Then how do I get the output? What is the response of such a system? The response of such a systems generally is given by the convolution of the input and the transfer function of the system. That is, it is x of t convolved with h of t, or I can also write this as equal to h of t convolved with the x of t. That means, if I convolve the input response with the transfer function or vice versa, the transfer function convolved with the input, what I will get is my output. So, the convolution integral is very, very important here. The convolution helps us in getting the output of a system given x of t, which is known function, and also the transfer function system which is also known function. Okay. So, here in the slides we are using convolution by the asterisk or a star signature. Now, let us look at various combinations which are available in the same convolution, how convolution is done. Let us take a non-causal signal, apply to a non-causal system. That means, system is non-causal and also the input applied is a non-causal. Then what will be the y of t? If you see here, if you have to be carefully looking at the integral limits, that is, what are the lower limit to the upper limit, that decides what is the system behavior for a non-causal signal for a non-causal system, and similarly we have to look at other similar functions. Okay. Now, let us see what is y of t here. Y of t is integral of minus infinity to plus infinity h of tau x of t minus tau d tau, that is equal to also minus infinity plus infinity, x of tau h of t minus tau d tau. As I said, y of t is x of t convolved with h of t or h of t convolved with x of t. If you look at the limits, this being a non-causal signal, the limits are from minus infinity to plus infinity in both the cases. The case here is what? It is a non-causal signal that is again applied to a non-causal system. Now, let us look at the second case. What is the second case? Second case talks about a causal signal that is applied to a non-causal system. So, system is non-causal, whereas the applied signal is causal signal. So, how do I get output in such cases? If you look at y of t here, which is the response or the output of such a system here is what? The signal input is causal and the system is non-causal. Let us see what is the output of such a response. So, if you look at this, y of t is minus infinity to t h of tau x of t minus tau d tau. So, we are starting from minus infinity to t because h of tau is involved first, then or else it is equal to 0 to infinity x of tau h of t minus tau d tau. So, this is the case of getting the output when the system is non-causal and the applied signal is causal. Now, let us take up the other case, that is a third case. What is the third case talks about? It talks about a non-causal signal applied to a causal system. So, I have a system which is causal, whereas the input I have applied is non-causal. So, if you look at h of t here, h of t is again integration of h of tau x of t minus tau d tau, or it will be integration x of tau h of t minus tau d tau. Both cases are same. The only difference is here the formula remains same, integration, but only thing that we have to look carefully at is the integration. So, when you look at such a system where the system is causal and the input applied is non-causal, y of t will be equal to 0 to infinity h of tau x of t minus tau d tau, or minus infinity to t integral x of tau h of t minus tau d tau. That is the third case. Okay. Similarly, let us look at the fourth case. What does the fourth case say? The system is causal, whereas the signal that is applied is also causal. Both are causal systems. That means the condition the system is in is causal, or causality is being maintained by a system. The input signal which I am applying is also causal. In such a case, what will be the corresponding output? Let us look at it now. So, what will be the corresponding output? Y of t will be equal to integral 0 to t h of tau x of t minus tau d tau, or integral 0 to t x of tau h of t minus tau d tau. Okay, this is a perfect case where both are causal. Earlier three cases we have seen both being non-causal, that is the system being non-causal and also the signal that is being applied non-causal. In the second case we have seen the system is non-causal where the input applied is causal. Third case we have seen the system is causal whereas the input applied is non-causal. And finally, the fourth case which we are right now seeing is both are causal, that is my system is causal and also the input which I applied to the system is also causal. In such a case, y of t is given by integral 0 to t h of tau x of t minus tau d tau, or you can also write this as 0 to t integral x of tau h of t minus tau d tau. Okay, so this is all these four cases which you have seen where the output in fact can be calculated from the convolution of the input and the system transfer function. As you see here, y of t is nothing but equal to convolution of x of t and h of t, or h of t and x of t. So, if it is convolution of x of t and h of t, the formula will be integral limits decided by the four factors which you have seen above, x of tau h of t minus tau d tau, or it can be written as integral, again limits decided by the above four conditions, it will be equal to h of tau x of t minus tau d tau. In both cases it is same, x of t convolved with h of t or h of t convolved with x of t. Let us look at the next slide. So far we have been looking at systems in isolations, like continuous systems in isolation, in the sense that we have not made any connection between the different systems. Now let us look at systems if they are connected in certain configuration, what will be the overall input versus the overall response of such a system. Okay, let us start with discussing about what is called as a cascade connection. Okay, let's look at a cascade connected continuous time systems. That means two systems are connected in cascade. Okay, that means the output of one system is connected as input to the other system, then that becomes a cascade system. Okay, now let us see this. Two cascade connected continuous time systems with impulse responses h1 of t and h2 of t can be replaced by a single equivalent continuous time system whose impulse response is given by the convolution of individual responses. So that's what this says. Cascade connection is what? You have two systems like this. I can connect these two. Okay. The transfer function of this is h1 of t and the transfer function of this is h2 of t. So this is y of t and this is x of t. Okay. Whereas this will have its own output, whereas that will also have its own output separately. But if I combine them, let us look at this in such a connection. So what does the slide says? It says it can be replaced by a single equivalent continuous time system, that is a CTS, whose impulse response is given by the convolution of individual impulse responses. That means if I know y1 of t and if I know y2 of t, that is the impulse responses, the total output will be the convolution of these two when I connected in cascade. Now let us look at the parallel connected continuous time systems. So what does this say? Two parallel connected continuous time systems with impulse responses h1 of t and h2 of t can be replaced by a single equivalent CT system, that is a continuous time system, whose impulse response is given by the sum of the individual impulse responses. So as seen here, let us think about two systems connected in parallel. Let the transfer functions of these two systems be h1 of t and h2 of t respectively, the first and second system. Now these two are connected in parallel. Then I can have a system which is an equivalent of these two systems connected in parallel, whose output is the sum of the individual responses. As understood earlier in the other type of connection, we have seen the total response is the convolution of individual responses when they are connected in cascade. But when they are connected in parallel, it will be the sum. So let us just read it again here. Two parallel connected continuous time systems with impulse responses h1 of t and h2 of t can be replaced by a single equivalent continuous time system whose response is given by the sum of the individual impulse responses. So there is an addition here. Earlier it was a convolution in that particular case. Now let us look at some very important points in which we have studied so far. Okay, we have been studying about different types of systems, whether the system is a causal, whether the system is a non-causal, a system is stable, system is unstable, and all those other things. We have seen about a feedback system or a non-feedback system, or we've spoken about a system which is time invariant, and we've spoken about a system which is time invariant. And also we have seen various conditions under which a system can be considered as a linear system. As you are aware, a system to be linear, it has to satisfy two conditions. One is homogeneity, the other one is superposition. So let us summarize all this together here and let us understand what all we have studied so far. So we have placed them all in certain points. So these points will help us in reminding ourselves what we have studied so far, and also will act like a sort of revision for us during the exams. Okay, let us start with these points. Let's start with the first important point. Okay, first point is an analog signal is a continuous function of an independent variable. So how do you define analog signal? Analog signal is defined as a continuous function of an independent variable. That means, let us say, okay, I have a system like this. This is an analog signal, this is a continuous function with an independent variable, some variable which we have yet to define. So this is called as a analog signal. It is a continuous function. You see, there are no breaks. It is a continuous function with a certain variable here, which can be either time, frequency, whatever. We don't know what it is right now, but it is a continuous time function. So its amplitude is varying continuously with time if you look at this. Okay, so this is called as an analog signal. The independent variable which you have spoken in point 1, if it is time, then I can call this as a continuous time signal. Okay, the individual time, isn't it? So this is independent variable. If I call this as a time t, then what happens? We can say that the signal is continuously varying with independent variable, which is time. Then such type of signal is called as a continuous time signal, or famously called as CT. So CT here indicates that it is continuous with respect to an independent variable. The independent variable for us here is a time, and this is an analog signal, which in fact is a continuous time signal. In a continuous signal, the magnitude and the independent variable are continuous. That's very important. Okay, here what is important here? How to define a continuous signal? Continuous signal is that signal where the magnitude and the independent variable are continuous. As seen in the earlier figure, both the magnitude and the independent variable time are continuous. That's why it is called as a continuous time signal, or in other words, it is a CT signal. Okay, let us look at the fourth point, very important point again. The sinusoidal and the complex exponential signals are always periodic. Take any sinusoidal signal, take any complex exponential signal, they are always periodic. This again another important point. Let us look at the fifth point. What does the fifth point say? The sum of two periodic signals is also periodic if the ratio of their fundamental periods is a rational number. That means if I add two periodic signal, the resulting signal will also be periodic if and only if the fundamental periods ratio is a rational number. So that means let us take two signals. Let us take one signal. Okay, this is my signal 1, which is, let us say, having a fundamental frequency f1. Then let us take at a second one whose fundamental frequency is f2. Okay, now add these two signals. Let us add these two signals. So this is periodic by itself, and this is also periodic by itself. So what is it I am doing? I am adding a periodic signal and another periodic signal. If I add these two, the resultant signal is also periodic. Okay, provided the ratio of the fundamental frequencies of these two periodic signals is a rational number. So unless until this condition is satisfied, we cannot tell about the periodicity of two periodic signals which are added. So this is an important point which we all should remember. So that's what, let's just summarize this again. The sum of two periodic signals is also periodic if the ratio of the fundamental periods is a rational number. So if you take the periods f for t, whatever fundamental period, if you take their ratios, they also must be a rational number. Then only I can say that these two sum is again periodic. Okay, let us move on quickly to the next point, important point. A signal is neither even nor odd, can be expressed as a sum of even and odd signals. So a signal is neither even nor odd and can be expressed as a sum of even and odd signals. Seventh point, periodic signals are power signals and non-periodic signals are energy signals. This is very important. Okay, so if you look at the periodic signals, they are all power signals, and when you look at non-periodic signals, they are all energy signals. So that's why, if you look at the Rayleigh's path theorem, it always talks about P is equal to 1 by 2t, that is a period. Okay, so an integration will be between those periodic limits, that is the power signal. So if I look at a power signal, it's generally a periodic signal, it's a periodic signal, and energy signal is a non-periodic signal. This is how we can classify different types of signals based on the type of energy available. Let us again, if I have a power signal, what will be? It's likely energy, and if I look at energetic signals, what is its likely power? Okay, as you have guessed it correctly, as we have studied earlier also, the eighth point actually puts us these points clearly. Okay, what does it say? The eighth point says the power of an energy signal is 0 and the energy of a power signal is 0. That means if I look at a energy signal, then its power must be 0, and if I look at a power signal, its energy must be 0. This is clear. That means a power signal will have zero energy and a energy signal will have a 0 power. Then let us look at our next point, 9th point. An infinite signal is a signal with infinite magnitude and 0 duration. This is very important. So how do you define infinite signal? Okay, if I say this signal is infinite, so how do I classify it? We say it is infinite when it has infinite magnitude and the duration is 0. Okay, a 0 duration, whereas the magnitude is infinity. Next, let us move on to the 10th point. 10th point says, practically an impulse signal is a signal with large magnitude and short duration. Okay, ideally impulse signal is what? Impulse signal will have infinite magnitude and 0 duration. But practically, how do you call impulse signal? How do I define an impulse signal? Practically, how do you define an impulse signal? Practically, an impulse signal is a signal with large magnitude and very short duration. Okay, so it cannot be infinite, cannot be 0. So it's the shortest duration and the largest magnitude, then it is called as an impulse signal. Let us move on to the next point, that is 11th point. The 11th point says, the homogeneous solution is a response of a system when there is no input, whereas the particular solution is a response for a specific input. So when I look at a system, we talk about homogeneous solution, or also we talk about a particular solution. When I talk about a homogeneous solution gives us the response of a system when there is no input applied, whereas the particular solution is a response for a specific input. So let us just summarize this again, the 11th point. The homogeneous solution is a response of a system when there is no input, whereas the particular solution is a response for a specific input. Now let us move on to the next point. Next point says, the free or natural response is a response of the system due to initial stored energy, whereas the forced response is a response to a particular input when there is no initial energy. Okay, again we are talking about two types of responses here. One is a free, the other one is forced. Free is also called as a natural response. So what is this? Let us read this. The free or natural response is a response of the system due to initial stored energy, whereas the forced response is a response to a particular input when there is no initial energy. If a system has an inbuilt inertia or inbuilt energy in it, the response we get from that type of system is called as a free or natural response. Whereas when there is no initial energy but the response is basically due to the type of input which I give, then this becomes a forced response. Okay, let's move on to 13th point. What does 13th point say? The response of an LTI system is a sum of natural and forced responses. Of course, isn't it? Any linear time invariant system response will be the sum of natural and forced responses. So you have a natural response and also a forced response. Let us move to the 14th point. What does the 14th point say? The response of a static system depends on the present input, whereas the response of a dynamic system depends on the present, past and future inputs. So you can talk about two types of systems, static and dynamic. Static system response depends on the present input, whereas the response of a dynamic system depends on the present, past and the future inputs. Moving on to the next point, there is a 15th point. What does this point say? The dynamic system requires memory, whereas the static system do not require memory. Whenever we talk about past, then we must have a memory. System which has a memory is also dynamic system, because dynamic systems must invariably have a memory built into it. That means a dynamic system requires memory, whereas static systems do not require memory. Okay, that's about the 15th point. Let us move on. Let us see the 16th point. What does the 16th point say? In time invariant systems, the input output characteristics do not change with time. Of course, when I say invariant means what? The input output characteristics do not change with time. They are only delayed. Okay, if the input is delayed, the output is also delayed, whereas the characteristics remain same. This is called as a time invariant system. Okay, 17th point. What does the 17th point say? In time invariant systems, if a delay is introduced either at the input or output, the response remains same. a delay is introduced, either the input or the output, but the response essentially remains the same. Okay, that is one of the important characteristics of a time invariant system. Then what about a linear system? We said earlier, linear systems will satisfy the principle of superposition. That means all those systems which satisfy the superposition principle are called as linear systems, along with the other condition that is mentioned in point 9. What does the point 9 say? The response for a weighted sum of inputs is equal to similar weighted sum of individual responses. So, superposition plus this response for weight. That means, let us see this. If let us say this is the response, the corresponding input will be a x1 of t. That means this is measured, weighed by a factor a, then the output is also weighed by the same factor. Okay, this is one property. Then plus again the individual responses, if I add them together, that becomes superposition. So, superposition plus this, that means both your properties 18 and 19, if they are satisfied, then the system is a linear system. Then the system becomes a linear system. Let us look at another thing which we are all summarizing this. Actually, we have studied this earlier, but let us see the summary again, because these are very important points which we are trying to remember. 20th point. In causal systems, the response depends only on past and present values of the input. That is a causal system. That means, if I take a system, let us say this is my present time t1, then this has a past here. So, from here up to this t1, your system is dependent. Your system is dependent on the past plus the present, then this is called as a causal system. Now, let us look at a non-causal system. So, what is a non-causal system? Opposite to what a causal system is. In other words, in non-causal system, the response depends on the future inputs. Let us move on to 22nd point. 22nd point says, in stable systems, for any bounded input, the output will be bounded. So, stable system, input which is bounded always results in output which is also a bounded. That is bounded input, bounded output, BI/BO. Now, let us look at a very important point in 23rd. The present output of a feedback system depends on the past outputs. If you have a feedback system output invariably depends on the past outputs also. Moving on, 24th point. The response of an LTI system is given by convolution of input and impulse response, which we have just seen a little earlier. LTI system, what is the response? Is given by the convolution of input and the impulse response. Similarly, the unit step response of an LTI system is given by the integral of its impulse response. The convolution operation satisfies the commutative, associative and distributive properties. Okay, 27th point. When LTI systems are connected in cascade, the overall impulse response is given by the convolution of individual responses. Impulse responses. 27th point. When LTI systems are connected in cascade, the overall impulse response is given by the convolution of individual impulse responses. If we immediately look at 20th point, what does 20th point say? When LTI systems are connected in parallel, the overall response is given by the sum of its individual responses. That means, if you connect two LTI systems in cascade, the output response, overall response will be the convolution of the individual responses. Whereas, if I connect LTI systems in parallel, the overall response will be the sum of the individual responses. 29th point. The inverse system is used to recover the input from the response of a system. That means, when I use a certain method to carry out the process of finding the output for a given input, then there exists a system where it's called the inverse system, which actually recovers the input from the output response. That means, if I use Fourier transform, then I will use inverse Fourier transforms to calculate my input. A very important point here, 30th point. The cascade of a system and its inverse is the identity system. And 31, that is the last point, it says, the deconvolution is a process of recovering the input from the response of a system. Use convolution to find the response of a system, then I do what is called a deconvolution to find out what is my input from the response of a system. So, these are some of the certain important points which I have summed it up here, around 31 of them in total for the last few sessions which we had on different types of systems. Particular emphasis was on causality, non-causality, feedback systems, stability of systems, and most importantly whether the system is time variant or is a linear or a non-linear system. So, these are some of the points which I have compiled together here, so that will be of use to us to understand or recollect what all we have studied so far based on these topics. Let us look at some fill in the blanks now. So, fill in the blanks basically are a little different from multiple choice questions in the sense that you have to directly guess the answer or get the answer correctly rather than guessing them. So, in multiple choice questions in fact we have a lot of assistance which we get in some cases or some confusion also in some other cases. But let us look at fill in the blanks. Fill in the blanks is like this, either 0 or 1. Okay. Let us see this. The first fill in the blank. The dash signal is continuous function of an independent variable. If you had heard the important points correctly, what is the signal called? The dash signal is continuous function of an independent variable, and the answer is of course analog. So, analog signal is a continuous function of an independent variable. Let us look at the second question. The dash signal can be represented by a rotating vector in a complex plane. So, what type of signal can be represented by a rotating vector in a complex plane? So, what is the answer? The answer is a complex exponential. So, a complex exponential signal can be represented by a rotating vector in a complex plane. That is a fill in blank, second fill in the blank for us. Let us look at third fill in the blank. What does it say? The sum of two periodic signals will also be periodic if the ratio of their fundamental periods is a dash number. We have seen this earlier. So, what is that? The sum of two periodic signals will be periodic only if the ratio of their fundamental periods is a dash number. So, it must be a rational number. So, if the periods are T1 and T2, the ratio of these, that means T1 and T1 by T2 must be a rational number. Let us move on. Question number 4, fill in the blank. When a periodic signal is sum of two or more periodic signals, then the period of the signal is given by the dash of the period of its components. That means, I have taken two periodic signals, I have added them, then I got a signal. Then how do I calculate the period of that signal? Is given by dash of the periods of its components. That means we have to take the LCM of the two periods so that I can get the overall period of my total signal. That is how I calculate the least common multiple. Fifth one. When a signal exhibits dash with respect to t greater than or equal to 0, it is called an even signal. So, how do you define an even signal for a signal which is defined for t greater than or equal to 0? Okay, it is called as symmetry. When a signal exhibits symmetry with respect to t greater than or equal to 0, it is called as an even signal. So, symmetry is very important in the case of an even signals. Now, let us look at the sixth fill in the blank. What does it say? When a signal exhibits anti-symmetry with respect to t is equal to 0, it is called dash signal. Symmetry, we said even signal. So, of course, whenever there is an anti-symmetry, it is called as an odd signal. So, when a signal exhibits anti-symmetry with respect to time t is equal to 0 is called as an odd signal. Next point, the periodic signals will have constant dash. So, periodic signals will have constant of which? They have constant power. Non-periodic signals will have constant energy. Now, let us look at the ninth fill in the blank. It says the dash signals are defined for t greater than or equal to 0. We have causal signals which are defined for t greater than or equal to 0. 10th question, when the sign of a t is changed in x of t, the resultant is called as a dash signal. When the sign of t is changed in x of t, the resultant is called as the folded signal. Okay, I will just see this on the board, how it is called as a folded signal. Okay, this is a signal. I will change the sign of this. That means I should make this negative. Then it will become like this. So, this is said to be a fold of this. It is called as a folded signal, because when I fold this, what will happen? The sign t is equal to positive is becoming t is equal to negative. Similarly, when I fold a negative t signal, it will become positive. So, this change of sign is called as a folding of signal. Now, let us look at the 11th fill in the blank. The 11th fill in the blank is as follows. The dash is the reverse process of differentiation. Simple, integration. We don't want to discuss further about this, but the reverse process of differentiation is nothing but integration. Now, let us look at the 12th fill in the blank. A signal with large amplitude and short duration is called as what? It's called as an impulse. So, impulse will have large magnitude and shortest duration. Ideally, the magnitude is infinite, whereas the duration is 0. Next, 13th fill in the blank. The response of a system for impulse input is called dash. The response of a system for impulse input is called as impulse response. Okay. How important impulse response is, we have seen earlier. Now, let us look at the 14th point. What does the 14th point say? The 14th fill in the blank says the dash system is governed by constant coefficient differential equation. The dash system is governed by constant coefficient differential equation. The answer is a linear time invariant system. The linear time invariant system is governed by constant coefficient differential equation. So, let us look at 15th fill in the blank. What does 15th fill in the blank say? The dash response is the response of the system due to initial conditions alone. The dash response is the response of the system due to initial conditions alone. I am reading it twice so that during this second reading and the first reading, you must be able to guess the answer before actually the answer is displayed. Okay, so that's the reason why I am repeating this 2 times. That will help you in visualizing or imagining or guessing or finding out the correct answer in between these 2 cases. Okay. As we have said, whenever there is an initial energy that is present, there is no input applied, it is called as a natural or free or 0 input. I have not applied any input, so it is a natural response. It is called a free response because I am not exciting the input with a sudden input. So, that is why this is called as a natural or free or 0 input. Let us move on to 16th question. So, 16th question says, the dash response is the response of system due to input alone. The forced response is the response of the system due to input alone. Let us move on to the 17th fill in the blank. The 17th fill in the blank says, the systems that do not require memory are called dash systems. The systems that do not require memory are called dash systems. So, static systems do not require any memory. Therefore, I can read this again with the answer. The systems that do not require memory are called as static systems. Let us move on to the 18th point. A system is said to be dash if its input output characteristic do not change with time. Time invariant. So, a system is said to be time invariant if its input output characteristics do not change with time. Let us move on to the 19th question or 19th fill in the blank. 19th fill in the blank says what? A dash system is one that satisfies the superposition principle. What is the system which satisfies superposition principle? As one of the conditions is a linear system. A linear system must invariably satisfy the principle of superposition apart from other property. Okay, so what is this? A linear system is one that satisfies the superposition principle. Now, let us say 20th question. What does 20th question say? A system E dash is one in which the response does not depend on future input values. A system is dash is one in which the response does not depend on future input values. So, this system is causal. A system is causal. It is the one in which the response does not depend on future input values. Any system which does not depend on future inputs is called as a causal systems, which we have been mentioning here. Let us move on to the 21st question. What does the 21st question say? When the output of a system is finite for any finite input, the system is called dash stable. When the output of a system is finite for any finite input, then the system is called as BIBO stable. That means input is bounded or the input is infinite, then the output is also bounded, so output is called as also finite, then we call it as a BIBO system, that is bounded input and bounded output. Let us see 22nd question. For dash of LTI system, the integral of the impulse response should be finite. Okay, it's almost same but a little bit differently asked question. So we are talking about a stable system. For stability of LTI systems, the integral of the impulse response should be finite. That means when I take the integral, then that should be finite. Then it will say it is a stable LTI system. Let's move on to the 23rd fill in the blank. It says, in dash system, the present output depends on the past outputs. The present output depends on the past outputs. So as I said, a feedback system. A feedback system output always depends on its past, because there is a feedback path that is going from the output to the input. The present output depends on the past output also. Then such a system is called as a feedback system. The next question, 24th question. The response of an LTI system is given by a dash of input and impulse response. The response of an LTI system is given by a dash of input and impulse response. The answer is convolution. That means the response of an LTI system is given by the convolution of the input and the impulse response. 25th question. In dash connection, the output of a system becomes input for another system. What is the answer? Cascade. So in a cascade connection, the output of a system becomes input for another system, which we have seen earlier when I have drawn this on the board. So if I connect the output of one system as an input of the other system, then that type of connection is called as a cascade connection. The output of the previous system becomes the input of the next systems, and such a system is called as a cascade system.